Okay, if the derivative exists, we say that it's differentiable, but if the derivative does not exist, then we say it's not differentiable. And here's a bunch of examples where the function is not differentiable. The first one would be any discontinuity. If it's not continuous, it's automatically not differentiable. So here you can see we have a jump discontinuity. A limit from the left exists, a limit from the right exists, but they're not equal to each other. So that's a jump discontinuity. If you had a hole in your function, it would also be not differentiable. An endpoint is also a spot where your function is not going to be differentiable. That's called an essential discontinuity. Now these three in blue, you'll see that the function is continuous at that spot, but not differentiable at that spot. So let's see what's happening. The first one, you have this sharp corner. It looks like the slope from the left is 1 and the slope from the right is -1. So at that spot, the slope does not exist. So we'd say when x equals a, the function is not differentiable. Okay, that one was a corner. This one over here is called a cusp. You can see that it's approaching infinity from the left. The slope is approaching -infinity from the right. So when x is equal to a, we would have to say that the slope does not exist. Now this one in the yellow, we're going to say it has a vertical tangent line when x equals a. You'll notice the slope from the left is equal to -infinity. The slope from the right is also -infinity. But if you remember the definition of a derivative is a limit. And if the limit equals infinity or -infinity, we would have to say that that limit does not exist. So for this one, when x is equal to a, we would say that it's not differentiable. Now I want to point out that the function can be continuous and not differentiable. The other way around is not possible. If the function is differentiable, then it must automatically be continuous. One way that I remember this is with DC comics, so that's the only reason why the DC is here. The order is extremely important. The D implies the C. So if it's differentiable, then that implies that it's automatically going to be continuous. Again, here's another example where it's continuous, but it's not differentiable. Sharp corner or a cusp. Okay, here it's asking us to do an average rate of change. You may also see it as difference quotient. But basically it's just the slope of a line that goes through 2 points when you know the 2 points. So for the first one, we'll do these 2 points. You do the change in y over the change in x. We get 1/5. Do it again. Do it again. And one last time. So there's really nothing hard to this. It's just understanding what it means when they ask you for the average rate of change. We're talking about an interval. So it's not going to be at a point. It's going to be from one point to another point, and that's just the slope of your secant line. This is something that we did in Math 1 or Algebra 1. Some of you even did it in middle school. Okay, this one's telling us that f is a differentiable function. So that means the derivative is going to exist. And they give you a couple of properties that's going to help you find your final answer. But basically, they want you to use the definition of the derivative to show that your derivative is 3x minus 2. Okay, when they say to use the definition of the derivative, you're going to start with the most common one. The limit as h goes to 0 of f of x plus h minus f of x all over h. Now I want you to notice we know what f of x plus y is, and we need to find out f of x plus h. So all we have to do is trade the y for the h. So right here we trade the y for the h. Right here we trade the y for the h. Right here and right here. Okay, so we can plug this in for the f of x plus h. Okay, after plugging it in, you'll notice that the f of x in the front will cancel with the f of x in the back. Okay, you might notice that this piece does not have an h in it, so we're going to want to separate that piece, but it can have its own limit. On the other one, everything has an h on the top, so you can factor it out and cancel it with the h on the bottom. After factoring it out, we can cancel it, And we're left with the limit as h goes to 0 of all this stuff. Okay, for this limit, we can just plug in the 0 for the h, and we would just be left with a 3x. For this limit, I want you to notice that changing just the x to an h isn't going to change anything. So if this limit is equal to 2, then this limit will also equal 2. The only difference was that this one has an h instead of the letter x. The first one had an x, the second one has an h. That's not going to make a difference. So this limit gives you 2. Don't forget the minus, and now you're done. We were trying to show that that derivative was equal to 3x minus 2. Okay, usually in math when you're done proving something, you usually put a little diamond. So I'm going to put a diamond there, and we're done.